Good evening, everybody. We'll officially get started. Thank you, everybody, for coming to this month's meeting of the Amateur Radio Experimenters Group. Very happy to see you all here this evening. Also very pleased to be able to, I should introduce myself to those who don't know me. I'm the Secretary, Grant VK5GR. Tonight we have David VK5KK and Iain VK5ZD, who've been playing at the trippy end of the microwave spectrum, and they'll tell us all about it. So I'll hand it over to David and Iain.
Thank you, Grant. Okay, so it's more of an information session because I think we've presented 122 here before, going back a few years. Yeah, so the first couple of slides are just a bit of a recap on some of the history behind this project, and Iain and I have been mucking around on 122 for 10 years now, I think, from something like that. Been lucky enough to learn from the experts in Austria, the world record holders over there, or former world record holders, Wolfgang OE4WOG. So 241 gigahertz, the final frontier, I've called the presentation. Bit of history. Up until 2019, we were using diode mixers, which was like a harmonic diode mixer. You pump about 100 milliwatts in at 40 gigs and put some 144 megs in, and you get about half a milliwatt of 122 out. And that's the good part, because the noise figure, the Austrians reckon some of their better ones are about 27 dB. So, shades of crystal sets and things like that. So the different projects on the left was the very first one we did. I think only did 2 or 3 of those, and that was what we first mucked around with. And I think we got up to about 8Ks on 122 gigahertz on those. The format, I changed the format to something that would fit in a 40 millimeter tube, because 40 millimeters is the size of a offset satellite dish bracket. And that was published in Jubis in 320. So that was probably the first serious 122 transceiver. They're a receive converter with effectively a modulated oscillator. So we typically use CW, although we can use digital modes. In 2022, I got hold of some 120 to 135 gigahertz chips from Indy, or they were known as Silicon Radar at the time. And that was the second article in 322 Jubis, which was the 122, 134. And to date, that's about the only one you can do. 3CV has published an article, but that didn't go ahead, that project. So there's about a dozen and a half of these around, a few in Australia and a few in Germany. It's quite workable. If anybody's interested in these, I do have spare chips tested on printed circuit boards. Reason being, Germans, their allocation is 134.928, right at the top of the band. About 30% of these chips actually make it to that frequency. So to help the guys out there, I went through and I've tested about 15 of these chips, and we yielded enough to give them chips that would comfortably lock when they're warm. If they're on a mountain, they all lock at -20, but when the chip's sitting there at +50, it does drift a bit. So the current one, I don't know how many people get Jubis, but part of the thing with Indy to get some discount on chips, I promised them an article. So in the Jubis coming out next month, there will be a full construction article on the 241 project. So 241 is the highest of our allocated bands. Above 300 gigahertz is free range. So 241 is an ISM band. Like a lot of the microwave bands that high, we have them because they're pretty useless for anything else. The history on the chip on this particular one goes back to 2022 when Indy said they were working on a on a 240 gigahertz chip for radar. These radar chips are used for level measurement usually. They sell a lot of 120 gigahertz chip, and that's available at quite a low price because of the volume. The 241 gigahertz chip is a lot more expensive. And I believe they've got one or two customers that use these for specialised measuring equipment. But at that time, they actually offered me a 300 gigahertz module, but looking at the specs and speaking to others that played with them, it really wasn't going to do anything for us. August 2023, Indy announced the first of the 240 chips, which is an 091, which has anything up to 45 gigahertz tuning range. So typically what they do with these is they're not necessarily locked to a single frequency. They use the receiver is a full IQ receiver, so they can use various modulation techniques for measuring distance at different frequencies. 2024, Indy released a second batch of 091As. I think they made 20 to start with, or yielded 20, then they did another 20. I was going to use the 091 chip, but they mentioned that they were going to discontinue it and bring out a new one. Okay, is that better? That's working? Yep.
I don't know where the noise is coming from, yeah?
Yeah. Sounds like we're
There's
close to the sea.
people that are unmuted need to mute themselves.
Okay. So the 091 was discontinued and a new 097 was to be released. So the 097 is a production one. And what Indy have done previously, they did this with the 134 chip. They had a pre-release chip, which was a bit of a disaster because it didn't work above 130 gigahertz. And we can go into that. We worked out what the problem is of that one. In some ways, I think we've had to work with limited data because we basically have grabbed these chips when they've been available before they're released. And in the case of the 134 gigahertz chip, they didn't get a customer, so they've actually deleted it. It's still available, but it's there's enough for amateur stuff, but they haven't continued with it. So the 241 gig project, I didn't do anything with until late 2024 when the 097 chips became available, September 2024. And so this is what the biggest problem, there was no technical data sheet for the 097. It was different pin out to the 091. But we've got a pretty good relationship with their development engineers. So they shared with me some of their engineering drawings and their pin-out stuff that they used with the fab. They use a third-party fab in Berlin to do this work. So they're actually I believe they're quite interested in what we do with these things because it's something which they're totally not used to. When we said that we had broken the Australian record and managed to work over 25 kilometres, the comment in German was, "You have blown my mind. These are designed for 5 metres," that sort of thing. But yeah, they're very, and they're quite interested in what we do because I think because they're attached to the Frankfurt University, it's sort of an educational thing. Some of the early boards I've sent over there for the university to play with, no idea what they did with them, but on 122, but certainly it was an alternative to what they have, which is really just a pretty simple development board. So that was the difference between two chips, but what they added was actually a RF detector and power control. Having power control on 241 is a bit mute because you want as much as you want to get. So that on all the versions, that pin is always held low, so we get maximum power, but it gives about 20 dB range. And apparently that's some experimental thing they were trying with the chip. It's actually quite a reasonably linear control. The chip is miles. It's like another generation better than the other chips we've been playing with. It's really been Quite an interesting chip to work with, and it would be nice if they did a version with the same architecture for the lower frequencies, but I don't think that's ever going to happen. The other thing is got an RF detector that produces with full power about 1.7 volts. You've got to think about that, haven't you? How do you? I believe it has some amplification, but it's quite reasonable control. When you turn the transmitter off, it actually does turn the PA off, so that the amount of bleed through power is about 40 dB down, and it still registers a little bit of voltage. So maybe it's like an offset thing. It's not it doesn't go to zero. I think Jared knows these chips very well. So, but it's certainly very useful. You can say how it works, especially if you don't have a spectrum analyzer that works that high. There's a degree of experimentation. A lot of it's been with the test gear. Because to be honest, all these things have locked straight away. It's been a case of cleaning them up and getting the work better. This is the block diagram of the chip. Now, the chip is in a little QFN package. There's a QFN 40. The other ones are 32 pins. So a few extra things out there, but it is a full IQ receiver. The VCO in the older chips is at 60 gigs here. They've used a 13 gig stamp, and it is a much better VCO. Even though we're multiplied by a factor of 2, we're getting not quite T9 notes and certainly good enough for digital stuff. Whereas we're using a high frequency reference and everything else and a good phase lock loop, but we've actually got at this point better performance on 241 than what we have on 122, 134. So we'll probably go back and do some more things with that. It's been by degrees of getting improvement, but the chip has been set up so you can use an internal VCO, which you can, if you want to, you can injection lock it. You can turn it off and feed in an external VCO. And the printed circuit boards I did were set up to do that. I've tried it once, and really the VCO that's on board is as good as what I could generate externally, and so wasn't worth the extra effort. But the 13 gig VCO is multiplied up. It's divided by 4 in a prescaler, so the output to the phase lock loop is 3.3 gigs. And then it goes through effectively times 18 to get the 241 gigs. And the last stage you'll see is a frequency doubler down where the receiver is. So it's a full IQ mixer. The IQ balance is very good. With no trouble, with just straight 90-degree hybrid, we were getting at least 16, 17 dB rejection of the unwanted mixing product. It has a single antenna, which was the problem with the others. They have 2 antennas, so the focal point is not exactly in the same spot. It requires you to use a combiner. The combiner introduces about 4 dB loss. This has a coupler and an antenna. My guess is that the coupler and the antenna are pretty inefficient on the chip. It works, but that's about it, because the power they claim that comes out of the transmitter, we're probably not seeing that. Not that we've got an accurate way of measuring power there. But that's all on a chip that is 8 millimeters square. And that's most of the transceiver sitting behind that horn there. Here's some of the data. We did eventually get a data sheet, and they did go do some quite accurate measurements, but if you read the fine print, it's all before the antenna, so it's effectively the what the modules they've used are capable of. So my guess is there's a few variables that limit our performance at this stage. Probably the antenna is the biggest one, but it's surprising. I'll show you some plots on my spectrum analyzer that I can get in a moment. The VCO is pretty good, very linear. That's a plot we did a couple of years ago when I first got them, because there was no data, just to work out the tuning KV, compared to the VCOs and the lower frequency ones, which have like a 2-to-1 variance across the whole range. That is clearly something that they use in a lower frequency SHF phase lock loop. So it was very easy to deal with. It was easy to get the optimization. What's the test setup look like to test the chip? So the chips when I did the first two, there's three in existence in the world, and they're all here tonight. So I managed to get from Japan a 110 gigahertz W-band head, which is quite sensitive at 241. And Ian, you've got your yeah. So the secret is, I think on all but the K band, they use the same diode and they calibrate them and do some different other things and so forth. But the reality is I can see 50 dB signal above the noise, close coupled in the chip. The chip antenna, it's not easy to couple in. So it's WR12, I think, waveguide, and there's a bit of capped on tape over the end so you don't blow up the chip. But it's with the waveguide hard pushed on the chip. It's no idea what the power level is, but it's 50 dB over noise floor. So yeah, you can do meaningful phase noise measurements. So that's the rig I use to basically check the tuning range, check some of the functions, learn a bit about chip, work out how it turns the transmitter on and off. Phase lock loop, it's the same circuitry. What I've done with all these, the main board that's in these particular units is the same for all the different chips. So the front RF board changes. The main difference is that, of course, the PLL filter and the parameters there. So that's in the end, there's been probably 4 or 5 goes at getting something which is pretty clean, and then using the charge pump to adjust it. So it's not this. You could get away with just a plain resistor network, but I've found using the op amp. I might put my glasses on so I can actually read the screen. It's too fine. It's an OP184 low noise op amp. And you just use the analog devices software, plug in the tuning rate, set the charge pump for mid-range, and let it calculate. And usually 1 or 2 goes, you sort of learn about what the characteristics are of the VCO and where the sweet spot is, and away you go. And the filter bandwidth, I think on this one it shows that this is an early one, probably shows it to be, can't see it. It's 120, it's probably 150 kilohertz. In the end, with charge pump adjustment, it's generally about 200 kilohertz filtering. Anything higher than that, you start to, it still works, but the challenge here is to get all the power in the single carrier. And you know when you've got it pretty clean because you can adjust it a fair bit and the noise floor can vary, but there's no change in the center carrier. Some of the early schemes I've seen done by others where the noise floor is only 30 dB down, there's more power in the noise than what there is in the central carrier, which is, I think we don't have to explain that to anyone here. That's not the best. Now, the phase lock loop reference, we was having a discussion about this before. So it's commercially available. They're about $20, $25. Nice clean voltage control crystal oscillator. They're a third overtone, so they're specifically designed for microwave sources. So for this, we use 120 megahertz. And it's the same size as the Nano. These main boards are all, there's no digital circuitry or processor on the main board. It just uses an Arduino Nano, actually the AREG, because the standard Nano doesn't have enough room these days for the code. And this sits on the underside, so it directly connects to the Nano. And it's a very simple ADF 4110 phase lock loop. Very, very narrow filter, I think about 18 hertz. And it's this with Matt, we had a 40 megahertz version of this, which Matt's used with SDRs. There's now an 80 megahertz version with the same oscillator. And for this 120 megahertz, the theoretical limit we can go with the reference is about 127 megahertz, and you can get 125. It costs $50. These cost $20 because they must be pretty common. But it's basically third overtone oscillator, nice and clean. And if you heard we'll do a demo a little bit later, but it's other than a bit of scintillation and Doppler and things like that, it's a pretty clean carrier. That's the plot down the bottom. And the limit of the plot is probably the limit of my measuring equipment. But yeah, so I think at 1 kilohertz, it's minus 107 dBc. The noise that is pretty close to the ratings for the oscillator. That's a look at the front board without the whole nine. So there's the chip, and they're designed to be vertically polarized with the writing up the right way. We discovered that on the very first one. So we had, apparently vertical's a thing. We found the lower frequency ones are a bit ambiguous because it's a fairly basic silicon antenna. These are polarized quite well, and they are true horizontal. You can turn it and get a null, not huge, but 10, 15 dB when you cross polarize them, which is actually quite amazing. So it probably says something about the quality of the antenna. But it's an antenna on a printed, on a substrate. It's got a bit of plastic to go through. So who knows what the losses are, but there's a signal there. The lange you see going up the top was the idea I had for coupling an external oscillator, but we've never used them. And the matching for the IQ is basically a pi matching, very simple. They're 500 ohms out, and it matches it down to 50 ohms. And you see a little white block there. That's a 90-degree hybrid mini circuits one, 55 to 90 megahertz hybrid. Some of the others I've done a little bit of fine tuning to get the balance better. This one we didn't even bother with it. It's the IQ output's pretty good. We're lucky in the fact that it's right at the design frequency, 240, right in the middle of everything, and just the mixer seems to work really well there. If you can go down to 225 up to about 260. Never really checked it, but I suspect it's perhaps the IQ isn't 90 degrees. That's how it's tested. So right up against the waveguide. A few people are interested in that 3D printed device. There's the link. Ian thinks I'm nuts because I've got about 4 of them, but they're very, very handy. And they've got TPU rubber grips. So if you had to buy the chip and pay full price for it, you'd realise why the whole thing needs to be in a vise and so it doesn't fall on the floor. They're not cheap. And a W band sensor. So that is a real signal on 241. And that's an early one. We've got a little bit better performance, but it's about 40 dB of the noise. There's another plot later on, which is the next slide, which is the very latest, where it's about nearing's about minus 46 dB down. So we've got to the point where lowering the phase noise, not increasing, there's no more increase in power. So the majority of power is in that center carrier. And it sort of lines up with what we found on 122, 134. You've got to get to about that level. Anything less than that, then you've got a reasonable amount of power in noise. And that noise spreads out, plus or minus 250 kilohertz. So it's not of much use. Minus 63 is what my uncalibrated sensor thinks it is. If I was to calibrate that for 122, that'd be about minus 33. Who knows what the level is? I'm thinking it's probably minus 10 or minus 15 or something. We don't know. And Indy don't know either. They can't tell me. But it works. And that's a phase noise plot. from 3 kilohertz to 3 megahertz. So sort of near in is now about minus 46, 47, and that peak at 200 kilohertz, slightly to the right, that's where the filter is set. And that's about the optimum. Just by changing the charge pump, we've sort of worked out that's about the optimum spot. To the right, it seems to flatten out, but that's the limit of my spectrum analyzer. That's internal noise. You would expect it to be, keep dropping, but really it's down minus 55. So it doesn't, who cares? Now, software. I've got these slides here, but Iain could do a live demo. You want to? Yeah. So we'll do a live demo of the software, but essentially we use Android mobile phones to drive these things. In fact, if your Android phone is capable of about half an amp out the USB port, you just power it off your mobile phone. So I'll swap over to Iain.
Just get this thing to life again.
Yeah. So we just use a terminal program. You can use a laptop, so that's what Ian's got to demonstrate, just using TerraTerm or something, one of those terminal programs. Putty, he's using Putty. Okay, I'll just...
Start it again, I think. This terminal program loses the plot when you...
I'll just go through there. There we go. So mode-wise, we use CW. And Iain has programmed up the same sort of messages as you have in WGS JTX, so 6 messages. So you can do an automated QSO by clicking on the buttons across the bottom. But we can do digital modes.
Right.
Okay, there we go.
Here somewhere.
There we go.
This one. Oof, I got one here. Oh well, I will. Is this one? Oh, this one's working. Cool. Right. This is a terminal program, Putty. And what you're seeing on the screen at the moment is what comes up out of this thing. It's chatting with the Arduino. And there are various commands you can put in, like T to go to transmit. That's just generating a carrier. Back to receive. That's the 2 most common ones we use. Put it in transmit mode, see if the other guy can hear the carrier at the other end. All being well, we come back again to swap over. There is a help option where you can get a list of all the available commands, and there's quite a few of them in there, as you can see. I'm not going to go through them all at the moment, but there's basically 3 categories of commands. One is operating commands. So you can, use various things to send Morse code messages. There's several preset messages in here. So if I go M1, that'll transmit a CQ with my call sign. And that's the actual transmitting of CW is done by shifting the frequency. I mean, it's a hangover from the 122 gig units where they were always generating RF. So the only way to key on and off basically is when you key up, you shift the frequency half a meg away so you don't hear anything. And this is doing exactly the same thing. So we've got 6 preset messages, 3 for one end, 3 for the other end. It's kind of like a WSJT QSO where you sort of, do a CQ, get a response, send a grid locator, 7.3, thank you very much, contact done. So it's all automated. You just feed in what the call signs are you want it to send and receive from, what grid square you're in, and off it goes. So, message number 3 might be this one here. So it's KK, this is 5ZD, and you are 599. There we go. Good signal. So there's commands for operating. There are commands for configuring. Like we have 4 preset frequencies, F1 to F4 are the ones you can mess around. Well, sorry. You did that. Yeah, there we go. F1 to F4 is 4 preset frequencies. So I can switch between them just by going, I want F1. So I'll use frequency number 1. And it puts the little arrow next to it to show where I'm TXing. Frequency 0 is the frequency the thing's on when you're receiving. So the IF is 55 megs, which you can see up the top there. That's what it's set to. You can change that. You can change any of these things. So there's 4 preset frequencies. I mean, at the end of the day, there's only 2 of us using this stuff. So it's not like, we need to QSY because there's a lot of interference or anything.
That's right. The significance of F3, that's where the maximum power is. If we want an extra dB, we go there.
Yeah.
Which is nothing.
F5 is, like I said, the key up frequency. So when you're in CW mode and you're not, when it's keying on and off, it'll transmit either 241.000.15 key down or 241.000.65 key up. Shifting the frequency.
So the frequency shift it locks within about under 10 milliseconds.
It's half a meg anyway. So that's what it's showing.
There's actually no chirp. It's quite interesting.
Very, the locking is virtually instantaneous for all intents and purposes. So there's configuration commands. I can change the IF frequency. 55 is what we've got these things set to, which is handy as well, because if you've got a rig plugged in on 55 megs, that's outside an amateur band. So if you went and pressed the mic button to transmit, nothing happens on the radio and you don't blow this thing up. It's quite useful. If we're doing the 122 gig units, they're 144 IF. I just leave the microphone unplugged from the transceiver because I don't want to risk hitting the button by mistake and feeding RF in, because you're just feeding it into the receiver. Not going to do it any good. It's not going to affect the chip at the front, but it'll bugger up the rest of the electronics around here. And third set of commands are for diagnostic purposes. So you can look at, I've got to remember what they all are now. 2.4. So 2.4 command, for example, shows you, what the charge pump current is, whether we've got we've got negative bleed enabled, the bleed current, what the prescaler is set to, and various other things. Down the bottom here, we've got the tuning voltages for the VCO. That's actually, as well as the voltage from the PLL going to the VCO, it also goes to one of the Arduino pins. So we can measure what the voltage is, which is quite handy, because if that goes too high or too low, then it means the chip's not locked. So you need to sort something out. Where are we? If I went, you can see it down the bottom there. It tells me what the VCO voltage is. I mean, even if I go to transmit, it doesn't change at all, within 2 decimal places. It's pretty much exactly the same. Oh, yeah, 0.01 shift. If I was to go to F4, which is a bit further up the band, now it's 1.22 volts. So as you can see, it's moved 0.2 of a volt roughly to go, what's that, 900 and something megs, So the volts, or the megahertz per volt, I should say, is huge.
Yes, it certainly is. Yeah, we could do one of the sweep. Do one of the sweeps.
I've got
there's a sweep function in here as well, and in the end, it replicates what I did manually, and it was sort of compare the chips. That we actually have 2 from the first batch and 1 from the second batch.
Right. This one doesn't want to go to 236.
Yeah. I think you find about 238.
This is trying frequencies one after the other, going in 50 megahertz jumps. And now the VCO is starting to creep up. So that's about the lowest frequency it will lock at. And that will just keep stepping up. And we'll find the highest frequency. I mean, that varies a little bit, but...
Yeah, the first one we had a pot, so we could adjust the center frequency. Now it's actually the course tune set at half the rail voltage, which is near enough to, it's 1.6 volts would be center, 1.1, 1.2 is fine. So centers are in about 244. Yep.
We've got an option for a 245 2 volts. We've got an option for a CSV format on this as well, so you can just copy all the text off the screen, paste it into Excel, and that's how they've got the graph of VCO voltage versus frequency.
Yeah, so the chip, the difference between the two chips, the later edition went to about 1.15 or something, but they're exactly the same curves, exactly the same specs. So,
this one here samples the VCO voltage. I've forgotten.
100% logs.
A few hundred times it just samples it. And if there's anything going wrong, sometimes we've had jitter on the VCO voltage where it can't quite lock and it wanders around a little bit. And, the minimum, average, maximum, they're all exactly the same. 0 variation, 100% lock. But in the past, when we've had issues, especially with the 10 meg reference not being quite right,
yes,
it shows up here,
Yeah, it's interesting that the 241 chip outperforms, even though it's twice the frequency, outperforms especially the broader 122, 134 one. That's all of those were set up so they're optimum 134. They actually put out less power on 122. That's another story. The 122 only chips are pretty good. They similar to this, but the performance of this chip is far better than what we expected it to be.
Another thing I stuck in there is command number 26, which flips the local oscillator to the other side. If you want to test how well the IQ is working, we can, you actually have to put in 26 equals and then the frequency that's on your radio dial. So when it flips to the other side, it knows exactly how far to move it. So you see exactly the same signal, but with the IQ the wrong way round, and you can see how well the IQ is actually working on the thing. And they're pretty good on these. They're fairly rubbish on the 134 chips, weren't they? Yeah.
Yeah, the 134 chip, I've ended up having to use a transformer coupling to get anywhere near the 10 or 15 dB is enough to get just best part of 3 dB improvement received. These are just no adjustment, just worked as they were. So I think we're lucky we're right at the design frequency for the mixes on these.
Now, when we actually did the record, which is currently
25.0,
yeah.
Yes.
We were actually going out to test some mods that Dave had done to the module here. And thought, well, this is a handy day. We'll go and do some tests, and it just happened to be the day with probably the best weather for this. Certainly last year, it was the one and only day where the weather conditions were that good for the whole 12 months. So we went out and we did, what was the first one? Around 8Ks or thereabout.
8.8, yeah.
What we actually do is we put a 122 gig module in and line up the dishes with that, because at that sort of range, 122 is blazingly strong, so it's easy to find it. So we line up the dishes on 122, then take the 122 module out and put the 241 in. That worked. So we did 8Ks. Then we did, I think we went to about 13 odd.
Yeah.
And it was like, yep, this is still working. Let's keep going. So Dave is at the same spot. He was up on Medlow Road.
Medlow Road,
yeah. Up above Elizabeth on the hills there. And I just kept driving further away. Next one was about 20 Ks and that worked still. So I went and found another spot on a road just off Port Wakefield Road, a dirt road somewhere. And that was 25 Ks away. And that one worked as well. I mean, it was getting close to the limit, I think. But I mean, the signals were still quite readable, no trouble copying the CW we were sending.
Just as the further we went, the more sort of scintillation and sort of atmospheric effects on the signal, even though it was 25 degrees C, 10% humidity. So dew point at Edinburgh peaked about -8, I think. And that was around about the time we did 20 Ks. It sort of started rising by the time you were near two wells, weren't you? I think.
I was out that direction. Yeah, it was just some random road. I thought I just looked at the map and said, that's 25 k's. We'll try that. Pick that spot there. But I think it was sort of like getting near the end of the day at that point, so we didn't bother to go any further.
But it certainly we didn't expect, because we in the back of my head I'd always thought 20 k's would be the limit, and that's probably what it would be under average conditions. Since we did that was November the 12th, we've improved the systems. A bit hard to sort of pick, but certainly probably have a little bit more power output. At this stage, the horns, you'll notice, are still 3D printed, coated with foil, so nowhere near optimum. The whole idea with that, I think we probably found the right design, so now we can sort of get one CNC machine, but it costs 10 cents to do that versus probably $100 to do a aluminium horn. The only challenge we came across is, even though it's got a single antenna, don't ask me why, but they offset it 0.5 millimeter from the center of the chip. So what the horn is actually offset from the chip. You'd think that's a problem, but it's not, because about 10 wavelengths in front, the wave becomes a parallel wave. And what it probably means is that we have a slight adjustment in the vertical. It seems to make no difference. It probably tells us our dishes aren't that good, but certainly we can put 122 in, pull it out, put 241 in, and don't have to touch it at all.
Yeah, and it works. So yes, we've to go further. Well, to extend the 122, Dave's building a 76 gig receiver to go in the dishes,
which is a bigger challenge than all this. Yeah. I've got a mock-up.
At the moment, when you're up to 20 k's, you can pretty much say, well, there he is, and we can use the telescopes on the dish to sort of point the dish in the right direction, and that generally works. But if you wanted to do 50, 60 k's or something like that, you can't see the other end in the rifle scope. It's just too far away. You just have a vague idea of where it is. So we're hoping to use 76 gigs, because we can generate plenty of signal on 76 gigs. So we've got just a simple 76 receiver that fits in the same format as these little horns do. Then we can line that up on the 76. Then we put the 122 in and re-peak it on that. Then we'll move to the 241, and hopefully it'll all be spot on.
Yeah. So at this stage, we've gone back to using an anti-parallel diode doubler. I was actually playing around with chips used for car radars. And I have had one working, but the problem we got is the amount of heat they generate, and because it has to be put on a printed circuit board like that, that unit draws it's running off 5 volts, probably about 460 milliamps, so only half an amp. So there's a fair bit of heat down the front. And we run them off maximum 6.5 volts and just use another step-down regulator with them.
Is there more slides?
Yeah, there's a few more slides.
All right.
So I'll go back to the presentation. So we've gone through these. I've actually decoded Q65 on 241. We haven't had a contact. We've certainly had it working on the lower frequencies. We've seen that. This is Q65, and this was some time ago before the latest mods, so it should now work pretty well, but that's a decode. My other call sign is VK5ZMK. That's Dad's old Z call. That's on the third unit, so we can tell them apart. But certainly decoded Q65. That's a really rough screenshot because it didn't do anything else. But that 60E worked. Sort of got 30D to work, but 60E seemed to be okay. There's a little bit of smear on the signal, but it was enough to certainly decode.
The digital modes, we feed the audio from WSJT-X or whichever into one of the Arduino pins. The Arduino measures the audio frequency, then reprograms the PLL to provide the required frequency shift to get each of the... That's how it's done.
But it's got to come in handy one day to get that extra 2 kilometers. We kind of think we can get to 30. From the farm to Coffhill's 30.5. So might be a AREG field day thing. I don't think we're any chance of losing the current record, but it'd be good to extend it out as far as is technically possible. So yeah, digital modes, JT4 we originally did, and that works pretty well. Q65, Ian's done a really good job. And we've had an FT8 QSO on, was it 122 or
122,
122?
Yeah.
So would you believe that's not the only one? The G's have done it as well, I think. So here we go. So I'll run through these. That's what it looks like. 40 millimeter diameter tube. The only reason I stuck with that because that would fit in a bracket that you use for offset dishes, satellite dishes. Here's some pickies, I think, from the day we did the QSOs out to 25Ks. So a lot of 3D printing. So the Cassegrain's 3D printed. And these were done with the old software. We've now made them slightly larger, haven't we? We've gone out to...
Yeah, a little bit bigger seems to work better.
Yeah. Reason for that, suspect, is that the horn is not quite as directive as what we thought it was. But as much as the Cassegrain seems like a challenge, it's not. Once you know when the Cassegrain is working properly and you've got it spinning on its axis properly, there's an M5 bolt in there, so you just screw it in and out, is you just have a gradual rise and drop in the gain, and you can move the horn in and out with no effect because you just have a parallel wave. It's in the end, you're either over or under illuminating the Cassegrain. An interesting effect we found with 241, Ian was playing around with it and he could pull the unit back, well back. And the signal only started dropping once, probably the edge, like the minus 10 or 12 dB points of the pattern started to hit the metal hole in the back of the dish, which is, I think, about 38 millimeters. 122, as you pull it back, it's broader, it would drop down, but you could have the thing about a foot behind the dish.
Yeah, and it was still working.
It was still
ridiculous,
working.
But anyway,
it's just, might say our dishes aren't optimum, but it was you can certainly see, once it got to a point, we haven't plotted the pattern of these horns. They're based on the 122 horn, and I suspect they're broader than what they really should be. So you've got plenty of room to experiment. The dishes are Edmunds solar heater dishes, so quite deep, F over D. So a Cassegrain's really the only way you can feed them properly because the focal point is parallel with the edges of the dish, being 0.25 F over D. But hot swapping from 122 to 134, as we mentioned, you just line up on one and you're there on the other. And that's been really reliable. It's other than probably first or second time we went out, every time we do that, we hear something. And then you just sit there and optimize things. So 3D printed antennas. The conical one was settled on, but the rectangular one worked equally as well. It was slightly less gain, probably because of the way I dimensioned it. There's a larger one I've tried there that was sharper. The one on the bottom left-hand side, that's a single, that's actually not on 241, that's on 134. Got a single tube waveguide adapter made up that we're using on Ian's lens antennas, the 60 gig lens antennas. That works quite reasonably well. We might actually log into your site directly if you want to do that. Yeah.
I'd have to hotspot the phone for, hotspot.
I can do it here. I can do it here.
Oh, right. Okay.
Yeah. So Ian's got this website that he's done. And here's some calculations based on 10Ks, yada, yada, yada. Let's do a live demo. Let's do that. Let's see what that does. Oh, no, it's not going to do it because it's on the other one to stop the show.
The website steals information from the Bureau of Meteorology, and I acknowledge them at the bottom of the page. So, I'm not doing it on the sly or anything. I say it's their data, but I add some additional calculations to it to work out the actual atmospheric losses at various microwave frequencies, 24 gigs up to 241 gigs. So it gives you a number in dB per 100 kilometers of what the gas losses are likely to be. This is in addition to the normal free space path loss. Pick SA, for example. Oh, what happened there? You lost it. Hotspot went off. There you go. Try again. Refresh. Anyway, yes, it takes numbers from the Bureau of Meteorology's observations, get the temperature, relative humidity, that sort of thing. I calculate the dew point. I calculate the absolute humidity in grams per cubic meter, because that's the number that actually counts, is how much water is in each cubic meter of air. So, you know, RH goes all over the place, but dew point fairly closely is tied in with the absolute humidity. So as a quick reference, we can use the dew point if the number's below zero, which it isn't at the moment. So, for example, at the RAF base, we have 10 grams per cubic meter or thereabouts. So at 241 gigs, we can expect, in addition to the normal free space losses, 346 dB loss per 100 kilometers. Well, it's about 3.5 decibels per kilometer per 1,000 meters, which is a lot.
Yes. So you can see further.
You're not going to break any records today at the moment, right?
No, but let's go back. Ian's got this search function, so you've got data going back.
Well, we can put in. We can put in.
Let's do. I think I'll put the exact time in. 6.
Somewhere around about there. Yeah. Boom. Right. That was the conditions at the time we were doing the record.
-8.
So you can see, you know, Edinburgh, 73 dB, 100K, you know, way less than the 340 odd that's we currently got at the moment.
Snowtown is quite interesting. It is up Lockhill Way. That's won't give too many secrets away because we're transmitting to the world, but it's probably where we'll extend things.
Problem is, this doesn't happen very often.
No,
you know, and it's not like you can just say, "Shit, let's drop everything and drive to Snowtown." You know?
Yeah, but Ian's got an email service. It's got level 1, level 2. So if it's level 2, it's like 3 bells at the fire station. Yeah, quick. So it looked good around midday. And I said, "Ian, do I go for a test?" He said, "Yeah, let's go for a test." And it just got better and better and better as the time went along. So and these are, the average is probably going to be different over the path. It's probably all over the place, but it was, the interesting bit, normally expect this to be a northerly wind, but look where the wind direction is. It's from the west and 13 kilometers. So that was very dry. I suspect it was more of an upper level dry air coming down sort of thing. Did actually have a bit more of a look into it. Just in case it happens again in the next 10 years.
Those conditions, that was the only day last year where they had conditions like that.
Yeah. Yeah. So some of the ones
rare.
Yeah. Over the hills definitely gets it. You have more Lee Creek, places like that. You'll see like Murray and all that. But
unfortunately, my helicopter's not working at the moment, so we can't just shoot out there at a moment's notice.
Yeah, exactly. And you need a helicopter because it's pretty flat. But there's some parts in the Flinders Ranges. Certainly Snowtown comes up quite regularly. It's one of those on the list, and Ernabella Picture, because Musgrave Range is up there, nearly 5,000 feet. It's Indigenous land, so it's not something you can go walking into. But certainly, the Flinders, there's and just the back of here out towards Blanchetown, so forth. Accommodation Hill out. They're all potentials. There's not much data out there, but you'll find on Wonderground a lot of the farmer weather stations, and I track a few of them around the plains, and the more reliable ones have got professional equipment. You can see some interesting patches of dry air. And the next one, is the Australian record. So it's been approved, and the certificates apparently are in the post, or have been in the post for about 2 weeks.
The check is in the mail.
So that's the exact locations down to 6 decimal places of where we were. And it was a visual line of sight. The problem we have when Ian's on the plains, he can never pick where I am because it's, all the hills look the same. But I had a pretty good bead.
Actually, I could pick where you were this time because there's like a little dip between the two hills and you're right in the middle of it. So I knew where to point.
Yeah.
But that doesn't always work like that.
Yeah. The scopes have got a reasonable, ×5, ×6. So, 10, 15 Ks, you can see the other car. So, and we've got them sighted in. We checked them again a couple of weeks ago, and basically it's the width of a hair difference. So you can generally line up. Okay, that's the end of. Actually, I'll just go one further. The problem we have with these solar reflectors is that they reflect the sun really bad. So I don't know if you can see it there, but around here, that's one of my older Cassegrains, but the 3D printing has been melted and it's got various burn marks. Now, this was just sitting in the back of the car. This is the Cassegrain I used on the record.
Yeah.
So it wasn't perfect.
Wasn't optimal.
Wasn't optimum. It was in the end. You sort of it probably wasn't quite straight, but over the problem we had on the day was that the sun was setting, and we're aiming into the sun. So we're literally, even though it wasn't right on the sun, there's this bright band of reflection. So it gradually melted the Cassegrain. So probably by the 25K one, this thing had these burn marks on it, and it actually was. You can see it's not straight.
That's the problem with an east-west path. Whoever's pointing west late in the afternoon, it's got the sun straight onto the dish. So I've had the same thing happen to mine. I just left. I was experimenting in the back garden, and I had the dish set up in front of the shed with the door open, and I'd gone off to do something and came back, and the Cassegrain's starting to melt because the sun's just moved a bit. And did the same thing with the optical as well. I left that in the shed doorway, and I went off to do something, came back, and there's smoke coming out of the wooden box. Oops, the sun's got
Yeah, so we haven't experimented yet at painting it, but I don't think it's going to cause any issue. Just put a thin layer of paint on there. Might actually improve the dish. Who knows? But you literally have to cover them up in the back of the car. Otherwise, and Keith 50Q here has the same problem. So I've printed out spares of these and always carry a spare just in case we have an accident and the 3D printing's hanging off one of the bits of all thread. Okay. That is the end of the presentation. Any questions? Yes.
Okay. I'll take questions from the hall first. So, Arthur?
Yeah, thanks. Great presentation. Just the technology used on the IC itself, do you know what they're actually making with, like gallium arsenide or?
Yeah, it's a 110 nanometer process, so it's pretty old fab plant. So fab plant's in, I think that's right, isn't it, Gerard? 110. IHB, yeah. So it's IHB. It is. I believe it's it's assembled from available stamps, for want of a better word. I suspect. So that's about as much as I know. Yeah, it would be silicon germanium. Yeah. Because the interesting bit is that there are amplifiers at 241 gigahertz there. So that's we call it spoofware, whatever. Yeah. So clearly it's skunkworks. That's it. Yeah. Clearly it's a technology that's available. The chips cost an incredible amount of money. I've been lucky because it sort of comes down to research and everything else. And but I won't mention the cost. You can come up and ask me later. But yeah, luckily I didn't pay full tote odds.
Okay, Steve?
Very good. Thank you, Ian, Dave. Excellent. when you're aiming, does Mirage come into it? Does that create any any QSB?
Yes.
Yep.
Yep. So a windy, as we went on this, we've had contacts up to 10Ks a few goes, but the one where we went to 25, the further we went, if there was any wind, you'd suddenly get this, this wobble happen, and you could just guess it's a wind or a moisture patch or something going through. So the further we went, the more scintillation there was on the signal, and the Doppler's incredible at this frequency. It's it's about the size of the wavelengths is 1.25 millimeters, so it's getting close to a water droplet size.
Okay, any other questions from the floor? Yep.
Dave, I was just wondering why you don't use a laser pointer for lining up the dishes like Tim does for the optical stuff.
Yeah,
Thanks.
that would work. It's still a bit careful with laser pointers, maybe a red light, something like that. It would be, to actually see the other person on a scope, yeah, it would make sense.
Having played with optical stuff with Tim, trying to see a light in the daytime is extremely difficult, because unless you haven't got it pointed in exactly the right direction, you don't see anything. It's not like you see close to it. Even at night, when we're trying to find each other, it's a case of one of us sits there, moves the light around backwards and forwards, like sweeping up and down like that, until the other guy goes, I caught a glimpse, then you can sort of like spin it out. But it is very hard to find a light.
Okay, any other questions?
Yes, and with the optical, sometimes that other light is a brake light around Port Wakefield from Mount Lofty. That has happened. I've been, sorry.
Yeah. With the reflectors you've got and the actual surface of the antennas you're making for it, do you think you're getting much loss due to the flatness or the smoothness of the reflector? Or not so much?
Absolutely, yeah. They're nowhere near perfect. When we do work backwards on calculation, we suspect their antennas are 10 dB under where they should be. They're still directive, but in the end, it's you're using about that much of the dish that's probably close, and then anything more than 10% variation, so 0.1, 0.2 mil. The Austrians all use machined aluminium dishes, and most of the dishes they use are 400 millimeters, which have been machined out of a block of aluminium. So the only way they did that, Michael DB6NT's got one. Then I think there's a total of 5, but they were all machined by a machinist who worked at a facility in Austria that did turbine blades for GE. Yeah, Rudy. Yeah, OE5BRL. So he machined himself a slightly larger. He found a cast aluminium ex-military dish that was at 1.2 meters. And because it was 40 years old, it had aged and everything else, and they had a flatbed lathe that's like 4 meters across, so he re-machined that, and that's what they used for the world record on 122. But yeah, the only way would be to invest in a block of aluminium. I don't think JLC PCB would probably do one that big. Give it a go. But yeah, that's the antennas and the horn. The horn, once we settle on a good design, we'll get that machine. So I think we'll get some gain on that. But yeah, the dishes they're not optimum.
Hey, any other questions from the room? Otherwise, we'll take a quick look on Zoom as well. Any questions from Zoom? Just unmute yourself if there are. Doesn't look like it. All right. Well, look, thank you very much, David and Iain, for showing us the presentation. I know there's a couple of dishes up the back of the hall here, so in a couple of minutes, while you're all getting your coffee ready for the general meeting, I invite you to see Iain and David's gear out the back there. Otherwise, thank you very much, everybody. Tea and coffee again over on the side. Thank you to David and Iain. On behalf of Amateur Radio Experimenters Group, we'd like to offer you a little gift in appreciation for your efforts this evening. So thank you very much for coming.